Graphical method. One of the simplest methods in solving an LP is the graphical method. It involves visually determining the feasible region of the LP and then finding the optimal solution from all feasible points in this region. However, being a method that relies on graphing, it can only be effectively applied to LPs having a maximum of 2 decision variables. It also requires that all constraints on the objective function be properly drawn to scale. Let us consider the following problem to see how the graphical method can be used in solving an LP. Maximize z is equal to 3x sub 1 plus 2x sub 2, subject to 2x sub 1 plus x sub 2 is greater than or equal to 2. X sub 1 plus x sub 2 is less than or equal to 8. 3x sub 1 minus x sub 2 is less than or equal to 12. X sub 2 is less than or equal to 5. And x sub 2 are both greater than or equal to 0. The first step in graphically solving an LP, be it a maximization or minimization problem, is to plot the constraints in order to find the region wherein the optimal solution may come from. This region is called the feasible region. For this problem, let us plot x sub 1 in the horizontal axis and x sub 2 in the vertical axis. Since we are dealing with only 2 decision variables, the graph of each constraint will be bounded by a line. To make graphing easier, we can first treat each constraint, except for the non-negativity constraint, as an equality. Therefore, the first constraint, 2x sub 1 plus x sub 2 is greater than or equal to 2, will be plotted as 2x sub 1 plus x sub 2 is equal to 2. Since we only need 2 points to draw a line, we can use the intercepts by letting each constraint be equal to 0, one at a time. In this constraint, if x sub 1 is equal to 0, then x sub 2 will be equal to 2. And if x sub 2 is equal to 0, then x sub 1 will be equal to 1. Plotting this constraint would look like... Now, we treat the constraint as an actual inequality, so let us consider the area bounded by the constraint. One technique is to check whether the origin is part of this boundary by substituting 0 to both variables. If we do this to the constraint 2x sub 1 plus x sub 2 is greater than or equal to 2, we can see that 2 times 0 plus 0 is equal to 0 is not greater than or equal to 2, which means that the origin is not part of the constraint boundary. Hence, we consider the region to the right of the line, and this becomes our new feasible region. Note that we've already taken the non-negativity constraint into account, so we only consider the region bounded by the positive axes of x sub 1 and x sub 2. For each additional non-redundant constraint, the feasible region becomes smaller. Doing the same procedure for the other constraints, will result to this feasible region. The next step would then be to find the optimal solution among the infinitely many points within the feasible region. To help us in this, it is important to remember that one characteristic of an LP is that the optimal solution comes from one of the corner points of the feasible region, which are the intersections of the different constraints. We then plot the objective function line. For this problem, our objective function equation is z is equal to 3x sub 1 plus 2x sub 2. To plot this as a line, we give any value to z. Let us try making z equal to 3, giving us the equation 3 is equal to 3x sub 1 plus 2x sub 2. After plotting the objective function, we move it across the feasible region to find the optimal solution. In general, for a maximization problem, we move the objective function line away from the origin, and the last corner point it touches will be the optimal point. For a minimization problem, we generally move the objective function toward the origin, and the last corner point it touches will be the optimal point. In our case, we move the objective function away from the origin, and we can see that the last point it touches is the point x sub 1 is equal to 5, x sub 2 is equal to 3. This is the optimal solution and would result to maximizing the value of z to 21.